So the treatment of phase field methods was the last on distributed methods for capturing fracture and failure. I'm now going to give an overview of methods which can capture cracks in a discrete manner. I will start with interface elements, discontinuous Galerkin methods, measureless methods, and after that I will carry on with extended finite element methods and isogeometric analysis. Now essentially we have most of these approaches, discrete approaches, use, not all, but quite a few, use again cohesive zone approaches. And we're going to talk first about interface elements. So we have seen that we have a traction which is a function of the crack opening displacement and history parameter. And obviously the limiting case is that you have no traction at all. So then you just substitute 0 for this. Now, the simplest possible way to implement discrete fractures is like this. Now here you have a continuum element, the blue. Here you have another continuum element. And here, the green, is an interface. A zero thickness interface. And, well, I have plotted so that this point, and this point are separate, but in reality they coincide. So here, this point, and this point are lying on each other. What you do is you give this continuum element its own degree of freedom, its own displacement degree of freedom, and this one also its own degree of freedom. Now when you look into this interface element, it is attached to this degree of freedom and to this degree of freedom. So over this zero thickness interface element, you can compute the difference between the displacement here and the displacement here. So you can compute over this interface the crack opening and in both directions the crack sliding. So like you have here assembled all the displacement degrees of freedom in this vector U, and now you assemble the crack openings in this interface in this vector V. Then this matrix L is filled by minus and plus ones. Because this contains this degrees of freedom here and here. So essentially, the crack opening V1 is the displacement here minus the displacement here. And for the sliding, it's the displacement here minus the displacement here. So here you have plus 1 and minus 1s. You interpolate the displacements in a standard way. So you interpolate them like polynomials contained in a matrix times the null displacements, and you retrieve your relative displacements at your interface as this matrix with minus and plus ones times this one, which contains the interpolation polynomials, times the nodal displacement. Now this is very similar to a standard continuum element, because you can there also now also multiply L with H, and you obtain a B matrix. Only this B matrix is different from the standard continuum B matrix, where you have ddx, ddy, etc. Yes?
What's exactly the difference between U and A?
U and
A. So V equal to LU, U are the nodal displacement.
this is the continuum displacement. This is the displacement at the nodes.
So what exactly is it?
Well, U is a displacement that can be anywhere in the element. And you, in a standard finite element way, you interpolate the displacement by polynomials times the values at the nodes.
Okay. So V is a continuous function, defined all over the element.
Yes.
Ah.
Yes. I mean, indeed, I pointed here at the nodes, but you can have V at any point in the interface element. I mean, essentially, indeed, you're very right. I should have phrased it more properly. V is the relative displacement at any point in the interface as this operator times displacement at one part of the continuum here minus the other part of the continuum here. And then the continua you just interpolate in the standard way, and therefore you bring V also back to the nodes.
Just to confirm, L is like both sides continuous operator. The input is also continuous, output is also continuous. But for H, the input is discrete and the output is.
These are continuous operators.
Operators.
I mean, like, compare it with strain is a matrix with differential operators times a continuous displacement field. Indeed. Just think in your head as epsilon is L times U, where epsilon has ddx, ddy, etc. Where it's just the strain operators. Now, you can derive a stiffness matrix for this interface element in very much the same way as you do it for standard continua. You multiply this B operator, the transpose, times the matrix you get for from your constitutive model, times again the B operator, and integrate this over your volume of your interface. In this case, in a three-dimensional configuration, a two-dimensional interface. When you have a two-dimensional body, you have a line. How do you get this? The T. Well, exactly the same as you get your tangent stiffness matrix for any constitutive model. So, let's go back here. Here we have, for instance, for our cohesive model, our traction as a function of your opening and your history. So, your T is just the derivative of the traction with respect to the crack opening, plus T with respect to the history, and the history is again then, of course, a function of the crack opening. So, this is exactly the same way how you derive for any damage model, any plasticity model, but then using strains and stresses. Here you do exactly the same using tractions and relative displacements. And the only thing is, the difference is that here V is a vector instead of a two-dimensional second-order tensor. I mean, now these interfaces, you can do two things. You can either put them a priori before the whole process begins, or you can do a kind of remeshing and insert them during the fracture process. The last one seems the more elegant one, but this was also, from a software point of view, the more complicated. So most people insert them a priori before the whole fracture process starts. The problem is, you have to do something with this stiffness prior to cracking them, because you have interface elements sitting there which should do nothing. Well, that's in principle impossible. So what you then do is you say, okay, for this T, I insert stiffnesses which are very high value. Sometimes they're called dummy stiffnesses, high dummy stiffnesses. In order that we prevent any opening with the N or sliding with the S and dt prior to crack formation. I mean, we don't want to have additional compliance of the total system prior to crack formation. I'll already warn you of a problem here. You should make them as high as possible in order to prevent deformations, but not too high, because else you get unwanted oscillations which will give you incorrect crack initiation. So for that case, if you then elaborate this, and I've done that, then you obtain something like your stiffness in a normal direction times vectors which contain the interpolation polynomials, and the same for both shear directions. Now here I show you this disadvantage with these oscillations. Here I have a simple notched specimen with a notch here, a point load here, and I just don't look at any fracture at the moment. I just place interface elements here. And what you then get is, you get obviously a singular behavior here. But when you increase the values for dn too much, you get these kinds of oscillations. So you capture the singularity better, but you also get these kind of things. So this is one of the things you have to be careful at when you are using these interface elements. When are they useful? When you know the quick propagation direction. One case where you quite often know that is in composite laminates. I mean, you know that the lamination will occur between the plies. So you here have just continuum elements for each of the plies. You connect them by interface elements between each of the plies, and you get perfect results. Here, this is a calculation where you very nicely see the size effect 1 over length, and in this even had experimental values, and you see that the computations are exactly in the experimental band. It was in fact a class A prediction because the computations were carried out before the experiment. So this is a case when you know where the fracture is going to be for some reason, and with denomination, that's often the case, you can use that very effectively. It's a very effective means, and almost all commercial packages have these interface elements available. This is another case. Here you have a strong backing plate here. There are some thin layers here. There is a round part where you don't have any attachment. You pull all around it, and what you see here is here you have buckling, and then you have nonlinear propagation of this initial round crack. So this is a similar case where you get good predictions, and these are supported by experiments. Another case is when you have an experiment available. For instance, when you know that the crack is going to propagate this from experiments or what other reasons, you can make a mesh, put interface elements along the expected crack path, and get results that are pretty good. Obviously, you must here know something about the crack path, because these interface elements can only be put between existing elements. I mean, it's the easy solution to discrete fracture, but it has the limitation that you have to align them with the mesh. And therefore, you exclude the possibility of a crack freely propagating. The other way, another approach, is to say, okay, I don't know anything about the crack. And Alan Needleman has done that, but I just put interface elements between all continuum elements. That's a good way to do it. However, there can be some mesh bias. For instance, when you change here the directions of the crack. So here you see it for different element layouts, that if you make the, in this case, triangles a little bit steeper, you get also steeper cracks. So there is some mesh dependency. You can do this. It is probably the only way that is a bit successful for crack branching using discrete approaches. There are some criteria around in the literature for crack branching in discrete approaches, but they don't work. At least they are not robust and reliable. With this kind of approach, some success has been made, but you see here also you have to be careful. Now, in fact, you can conceive interface elements as a special case of what is called discontinuous Galerkin methods. And discontinuous Galerkin methods are not so popular in solid mechanics. They are very popular in fluid mechanics. And, well, normally you're used to finite elements that have the same a priori for an element from here and an element from here, the same node here. You can also say, okay, I don't do that. I have an element here with its own nodes. I have an element here with its own nodes. And I try to find a smart way to connect those nodes and to connect those nodes. Well, in that case, we have this. This is for the interior of an element. This is for, and that means that around each element you have the volume and also the boundary integral for each element. So you have the volume here, and you have here the plus boundary and the minus boundary, if we integrate just over all the elements. Now, the big question is, what do we assume here? Well, one possibility is that we assume that the displacement is continuous and that the traction is equal to minus the traction from the other side. So, and then how we do that? Well, if everything else fails, you use Lagrangian multipliers. So you can do that. You can assume the Lagrangian multiplier to be t plus and minus t minus. So when you go to this, here you have lambda, here you have minus lambda. So this becomes lambda here, unknown. Here you have the difference in the displacements here at the boundary. And you have to supplement that when you use a Lagrangian multiplier with such a type of additional equation. So that's one way. You can also say, okay, I try to enforce this pointwise. So then we directly substitute here for the Lagrangian multiplier the interface traction. And then when you elaborate that, you get this, and this should be reminiscent of the tangent matrix which we previously derived for the tangent matrix for the interface element. So you can say these interface elements are nothing but a special choice of discontinuous Galerkin methods. And as they do it in fluid mechanics and many other cases, they say, okay, we have half times the normal times the average of the stresses at both sides, then we elaborate a bit, and then we have to add some things for proper condition and for numerical stability. The whole thing becomes a bit complicated, but it also works. Now, here you see a typical example of elasticity, and here even you can do some branching. So you can work with that. It's not popular in solid mechanics, except for the interface elements, which can be viewed as a special case. Another approach is measureless methods. Well, traditionally, you have here a finite element discretization. That means that we make a number of elements here. So here we have a number of nodes, and this element is connecting all these four nodes. When you look, conversely, when you look at this node here, this node is having shape functions non-zero in all the great domain here. So this is called mathematically the support of this node. The gray area is the support of the node, the area where shape functions are non-zero. Now in the finite element method, this support is directly one-to-one tied to the elements that surround a node. You can decouple that. You can also say, okay, I take a node and I choose a support with a shape function, for instance a Gaussian function, where this shape function is non-zero, for instance here. And I do that for every node. Now what you see then is, in this case, we can have overlapping shape functions, because this has this area. This one is also in this area, but has its own area, which is overlapping with this one. So what you do now is you say, okay, my displacement is some monomials, x squared, x cubed, as high as you want, times some parameters. And then I make a so-called moving least squared sum, which is a weight function, times this one, the interpolated function, minus the true function. I square that in a least square sense, and I minimize it. Just least squares approximation. So you have here this quadratic form. You differentiate it, you minimize it, you differentiate it with respect to your parameters, and you obtain this expression. So if you differentiate this with respect to A, you get this expression. And then you can manipulate a little bit again, and you obtain your displacement as these functions times a matrix A inverted, this matrix, which has the weight functions, and again these monomials, times this C matrix, which contains again the weight functions and the monomials. So now you have your shape functions, and you can compute it. It has some advantages. You don't have connectivity. You have future and force. You can just put nodes wherever you want. Remeshing is easier. Well, everything comes at a price. You still have to integrate. So in finite element methods, your integration cells are coincident with your finite elements. So you don't have that, so you have to do something extra with background integration cells in order to evaluate these integrals. And here I've already written them as sums. In addition, finite elements have the very nice property that their value, their interpolation, is 1 at the node. Which means that you can easily impose Dirichlet boundary conditions. In this case, you have multiple nodes in this domain, which means that the imposition of Dirichlet boundary conditions, just that your displacement is 0 here, or that you impose a displacement here, which is so convenient and easy in finite elements, is not so easy anymore in measureless methods. But there is a relation. If you go to low order monomials, so to low order functions in this P, and to weight functions with a very small support, then you retrieve almost the finite elements. And you see it here. Here it is still a bit distributed, but here you almost already go to the head of a linear interpolation triangle. Now, how do you cater for cracks here? That's also an interesting one. Originally, measureless methods were very much proposed as something where you can do easy remeshing, where you can easily propagate cracks, where you can also enormously easily add the singularity functions of linear elastic friction mechanics to your base vector. I mean, in principle, we started with monomials, so 1, x, x squared, x cubed, and so on. But there is nothing against extending this p vector with singularity functions. So you just add the 4 independent singularity functions of linear elastic friction mechanics. No problem. There is a problem for this integration. Because a crack is essentially a non-convex, a concave domain. Now, you have to integrate. Suppose we have a crack running here. We have this node with, suppose that this is the domain of influence, the domain on which its interpolation function is active. It would be a little bit weird to have the integration also over the great part here, because it's the other side of the crack. I mean, it's not realistic or not physical to assume that there is a relation between this part and this part. So, in this case, it's fairly simple. You just integrate only the shape function over this part and exclude simply this part. But it becomes a bit more tricky when you have a crack that runs into part of a support. So, what do you do here? Well, they've come up with 3 solutions, neither of which is really good. One is just do as if nothing has happened. So this is the so-called see-through criterion, where you just integrate over the whole domain, as if this part contributes as much. Well, that's not very accurate. This divisibility criterion is already much better and is used in most computations, where you exclude this great part. So here you have the node, you draw a line to the tip of the crack, and then further and you exclude this great part. Well, if you want to be even more accurate, but at the expense of quite a bit of extra effort, you can have this so-called diffraction criterion, where this line diffracts around this crack. Again, there is no real good solution, but these are the approaches that are being used. Well, this is an example of computation. It's a 3-dimensional computation. Here you have a linear elastic friction mechanics calculation with an initial penny-shaped crack in a square cube, or in a cube. Yes. Here you see it growing and growing, and here you see how it finally goes into 2 separate bodies. You can also combine, and that's quite good idea in fact, these meshless approaches with gradient damage approaches. And why is that? Well, unlike finite elements, you don't suffer from the problem that you need, that they are restricted to C0 continuity. You have no element boundaries, so the C0 element boundaries don't exist. And these bell-shaped functions, which are normally used, are usually differentiable for quite a number of times. So if you have higher order derivatives, no problem. So they are very suitable, for instance, to to combine or to use within gradient damage approach. And here we have done some calculations for a bar with second order, with fourth order, with explicit, with fully non-local approaches, and this works in those cases enormously smooth, enormously well. The only little headache you get is the boundary conditions, because that's a bit nasty. Here you see it also in a two-dimensional context. Here you have a 3-point bending bar. The load here, supports here. We take only a half with a symmetry boundary condition here, and we put nodes like this. We have a fourth order gradient damage model, and you get results that are very well converging. So this is in my mind, one of their big problems, big advantages. They have a high degree of continuity, which is ideal for higher order models, gradient damage, gradient plasticity models. Refinement, a local refinement, is extremely simple. You just put in some nodes, the shape functions come with them, and you're done. Most of the methods, and I emphasize most of the methods, need a background cell for the integration of the integrals. There are some schemes which have a null integration, so which have integration at the nodes. But this may not always be that accurate. So Gaussian type integration with background cells is usually to be preferred. Now, the Lect boundary conditions can be problematic. Again, there's a host of solutions. One of the obvious solutions is again Lagrangian multiplier using. Yeah, it's a point of attention. Remeshing is simple, but when determining the domain of influence, especially when the domain is not convex, and like with a crack protruding into something, that is, yeah, you have to pull some tricks there. But in principle, it's a method that is suitable for discretization of discrete grid propagation, but also for smeared approaches. And although it was originally proposed in the context of discrete grid propagation, linearistic friction mechanics, in my mind, smeared approaches like gradient damage combined with measureless methods are the more powerful approach. To the best of my knowledge, it has never been combined with nonlinear friction mechanics such as cohesive zone models. And I think I would like to, because it connects very well, now directly go on with the extended finite element methods and the isogeometric analysis. So, extended finite elements. Well, the extended finite element method relies on the property that the shape functions, the polynomials in finite elements, satisfy the partition of unity. Now, what's that? Think of just a linear interpolation, just a one-dimensional element, which a linear interpolation here from 1 to 0, and another one here from 0 to 1. if you sum up these two shape functions, they are together one everywhere. These two shape functions are a partition of one. They are part of one. Together, they always sum up to one. And obviously, for linear, it's easy to see that. But this holds for any polynomial. So for quadratic, the quadratic Lagrangian functions, for cubic Lagrangian functions, for quartic Lagrangian functions, this property also holds. So when you sum the shape functions over the domain of a finite element, and it holds for 1D, for 2D, and for 3D, they always sum up to 1. And in fact, that's a property that is shared by many numerical schemes. For instance, in the functions that we just used for the measureless approaches, it's also the case. These monomials in this P vector contained there are also a partition of unity. If you then manipulate them and come at the final function. Now, when a set of basis functions satisfy this partition of unity function property, you can add other functions. So, originally, we interpolate our displacement as our interpolation polynomials, phi, times the values at the nodes, the nodal values. So it's a sum of I from 1 to n of phi I times a bar, ai bar. Now, if these satisfy this partition of unity property, you can prove that you can add other functions to this nodal value. So at each node you can define other functions. For instance, these psi j functions. So at node I you can define m other functions. Now, for instance, what you now can do is related to linear elastic friction mechanics. At each node, you can add those 4 singularity functions of linear elastic friction mechanics. And then this way, try to capture the singularity, which is very hard to capture using normal polynomials. So what you do then is at the crack tip, you enrich this by injecting singularity functions. So, going to finite element notation, we interpolate our displacement field as our interpolations, our polynomials, times our standard displacement, nodal displacements, plus another matrix which contains these additional functions. For instance, these singular functions. Of course, they have their own degrees of freedom. And note that here, for those ones, you have a multiplication. So when you when you elaborate it, U is equal to capital H times A bar plus capital H times capital H tilde times A tilde. The null displacement, the displacement parameters related to the additional functions. But you multiply the additional functions by the original polynomials, and that has the advantage that you keep this enrichment local. You keep it, if you have one node here with surrounding elements, they are non-zero only for the support of these elements. So these singularities, functions, the additional functions, are only there in the surrounding of the enriched node. So farther away, they don't bother. You only have them there, and it's a big advantage, and you want to have them. You don't need the singularity functions far away. Now, this can contain singularity functions, but it can also contain other functions. And another function is, for instance, this one. The Heaviside function times the unity matrix. And when you insert that into here, you have H times A bar plus the Heaviside function at this discontinuity times H times A tilde. So essentially, you split your displacement field in a rigorous kinematic way into one continuous displacement field plus another continuous displacement field, but separated by a Heaviside function which is exactly placed at the discontinuity of the gradient. So this is the whole idea of extended finite elements. Now, when you are doing linear elastic fracture mechanics, you have to do a mix of those. Suppose that your crack has gone to here. Then in the part where the crack has already appeared, you put Heaviside functions as enriched functions. And at the crack tip, you enrich the interpolation with singularity functions. Well, I've said for cohesive zone models, you don't have a singularity, so their life is simpler. You only have to enrich the cracked part, the fully cracked part, and the partially cracked part with this Heaviside interpolation. Now, how does it work? Well, as usual, we have our balance of momentum. We have our interpolation of our trial functions, but we also have our interpolation of our test functions. And we do that in a strict Galerkin sense. So we interpolate the test functions in the same way as the trial functions. So we also interpolate them as one smooth field plus another smooth field, the continuous field, separated by the Heaviside function. Or at the crack tip for linear elastic fracture mechanics, we here then enrich it with the singularity function. So you get two fields, W tilde and W bar and W tilde. You can separate them, you get two sets of coupled equations. One related to one displacement field, to one side of the crack, one related to the other one, and at the crack tip you have the jump, which in case of a cohesive zone model you can use to feed your cohesive zone model. Now, there is a strong relation between these extended elements and the interface elements. In fact, interface elements can be regarded as the limiting case of extended finite element method. Because if you place so in principle, the discontinuity can run anywhere through the element. But if you put it at the edge of the element, then you can elaborate this, that you get the stiffness matrix of an interface element back. So then it gets a limiting case of an interface element. Now, it would be wrong to say that it is the same as an interface element, because in the extended finite element method, we propagate the crack during crack propagation. So we sort of generate, so to speak, the interfaces on the fly during propagation. So the whole issue of having infinitely stiff dummy stiffnesses prior to cracking does not arise at all, and therefore also not these traction oscillations. Well, this is an example of a linear elastic fracture mechanics calculation using XFEM. What we have here is a rectangular specimen loaded in tension here, which has an initial crack here and here. So an initial kinked crack. So let's zoom out in this area. And then you see here the crack. You see here that we have meshed it such that we run through the elements. And all these elements, where the square nodes are, these are enriched with a Heaviside function. Because there we have a fully open crack. Here, this element, where the crack tip is in, we have enriched with singularity functions. Because here, we want to capture the stress singularity. So all these elements here, we have enrichment of the Heaviside function, and here, these three nodes, we have enriched using singularity elements. This is an example of a three-point bending test using cohesive crack propagation. So since it's cohesive crack propagation, we don't need a starter crack. We can start with an entire specimen. And here you see some effects of mesh refinement. What you see here is some bumps for the coarser mesh. And this is related to the fact that you propagate, in that case, the crack through one element, and if this element is too coarse, you get a little bit of wobbles here, which disappear when you refine the mesh. So, how do you do it in cohesive crack propagation? Especially when you have heterogeneous materials. Well, you nucleate a crack, you look into the integration points. When some criterion has exceeded there, and here we have used a quasi-brittle material, a ceramic material, we looked at the principal stress direction, which is then reasonable. We initiate the crack here. And then, at some point, we look here and we propagate the crack here. And we propagate the crack here. But you can also have crack joining or crack branching in these cases. Here, this is a case of dynamic loading a so-called Kalthoff specimen. So you have, this is the symmetric part, so here is free. There's an indenter hitting here, there's an initial crack here, another initial crack here, and then the free part here. So here you see our simulation, which we did using XFAB. So you can do these things. I mean, this is, and the inclination angle is roughly the same, around 70 degrees, which was also observed in the experiments. Now the last bit, the most modern bit. Isogeometric analysis. What's that? It's essentially replacing the Lagrangian polynomials, which you normally use in finite elements, by so-called B-splines. And don't tell me that you've never worked with B-splines. Who has never worked with the cut package? All cut packages are based on B-splines. So, how do you define B-splines? Well, let's first show it graphically. In case of linear basis functions, there's no difference between Lagrangian functions and B-splines. This is the Lagrangian functions of a linear, one-dimensional finite element. These are the B-splines of linear, these are the linear B-splines. So you start from the same point. But when you go to higher order B-splines, you get differences. I mean, here you see the Lagrangian polynomials. And here, the red one, the dark blue one, and the green one are the B-splines, the quadratic B-splines. Now there's one thing which you immediately see, hopefully, and that the B-splines have a so-called non-negativity property. You see, Lagrangian become negative here. Higher order Lagrangians. Higher order splines will not become negative. And especially when you go to dynamic analysis, this is a huge advantage, because when you construct, for instance, the mass matrix using Lagrangian functions, you have all sorts of negative entries there. When you do the same using B-splines, you don't get negative entries. And that gives you much better behavior. Now, how does it work mathematically? Well, again, we have some function A, which we interpolate with B-spline functions, the n here, and we have some parameter. Again, it's an interpolation function times its magnitude. And here, Ni is the ith B-spline of order P. And these are the magnitudes of them, which are measured at so-called control points. And these control points are usually not nodes. So they are defined recursively. So for a simple constant B-spline, it is 1 at a domain and 0 outside. Same as for Lagrangian functions. Then for higher order ones, they are defined recursively. And the B-spline function of I of order P is this interpolation times the one of one order less, plus here for the other node of the order less. Well, for linears, it just gives this behavior, same like Lagrangian. But for quadratic, cubic, it gives different ones. Now, in fact, we don't use B-splines. And in fact, in cut packages, they don't use B-splines, they use NURBS. And NURBS are made out of B-splines. But they're a little bit more sophisticated, in the sense they are made by weighting them. So here you have your B-spline interpolation, you multiply it by a weighting function, and normalize it again by the sum of the weighting functions. Now, the advantage of that is that you can exactly capture certain geometries, like spheres. I mean, there would be no hope to ever exactly capture with a Lagrangian polynomial a sphere or a circle. With NURBS, you can exactly capture a circle, which has, of course, advantages when you want to describe a complicated geometry. For instance, when you want to model bone or something like this, then I can tell you NURBS have a big advantage compared to Lagrangian polynomials, because you don't introduce artificial stress concentration. Because with finite elements you have a little bit like this, which gives you an artificial stress concentrator. Not so with NURBS, there everything is totally smooth. Now, NURBS, or B-splines and NURBS, are essentially defined in one dimension. How do you do 2 dimensions? How do you do 3 dimensions? Well, do NURBS in each of the directions. So you just make a tensor product in 2 dimensions or in 3 dimensions. You just have a NURBS in this, times a NURBS in this, times a NURBS in this direction. So you then, for 2 dimensions, you get a double sum. For 3 dimensions, you get a triple sum. Times here the parameters, which are these control points in 1 dimension. Sorry. Now, a nice thing. These B-splines and NURBS do satisfy the partition of unity problem. So that opens up, in principle, adding singularity functions, adding discontinuities. Life is not that simple, but in principle it's possible. So that's nice. The next one is less nice. We have a tensor product structure. So you have interpolation in this direction, times 1 in this direction, times 1 in this direction. This prevents you from local refinement. So that's the disadvantage. There are ways around that, but I will not go in, which are called T-splines, but I will not go into that. That's really going pretty far. But they have some nice properties. You can very easily go from linear to quadratic to cubic NURBS. That's a very easy process. And the nice thing is, you get higher order continuity, not only within the element, but also at element borders. So at Lagrangian functions, you always have at the element border C0 continuity. Not here. If you have a NURBS that is second order, and therefore C1 continuous, which means that the function is continuous, but also the slope is continuous. This holds inside the element, but also at the border of the element, at the edge of it. Now, for structural engineers, displacements are interesting maybe, but the stresses are the most interesting. Stresses are obtained from displacements, and displacements are obtained by differentiating, stresses are obtained from strains, and strains are obtained by differentiating displacements. So if at some point you have a C0 continuity, a kink in the displacement field, this means that when you differentiate there, you have a jump in your strain field. This means that you have a jump in your stress field. In practice, and definitely around correctives, this means that you have a messy stress field. This means that if you go and do the same calculation with NURBS, that your stress field is much smoother. And definitely around correctives. It's an enormous difference which we have found. And in fact, this not only applies to stresses, it applies to any derived quantity. For instance, here I have a typical coupled problem, where I have deformation of soil coupled to flow of water. So a typical consolidation problem. Now, the important thing here is the flow of the water. Well, you interpolate the displacements and the pressures. The flow of the water is obtained from the pressure gradient by Darcy's relation. Now, when you do this with standard finite elements, you get this staircase behavior when you have finite elements. Essentially, your pressure is piecewise continuous, and therefore you have a discontinuity, your pressure gradient, and therefore you have this staircase, and therefore, since you have here a different value for the water flow than here, you have a loss of local mass conservation. Lots of efforts have been done to repair that, but if you have just a high order NURBS, and here we use only 3 NURBS, contrast to the 8 finite elements along this column, then you get it automatically. So any derived quantity is captured much better. The other advantage is that you get a new way to insert discontinuities. Because I told you that you have the possibility to very simply go to higher order NURBS. And you can go from linear to quadratic to cubic and so on. Similarly, you can easily lower the order of continuity. And if you have somewhere a C0 continuity and you lower it to a C-1 continuity, you have a crack. Because that means that there's a jump in your field. So you can exploit that. And essentially, that is what is shown here. You can do a knot insertion to lower the order of continuity. But you still have the good old interface elements, which you can also formulate using NURBS. And you can also formulate splines directly on triangles. There are some buts still, but you can do that. And you can try to marry the best of two worlds. You can try to combine XFEM and IGA. And then you get an extended IGA where a crack can run through an element. These things are at the moment quite a bit in development. It's not that trivial because one of the issues is that, like measureless methods, NURBS have a little bit of a problem with Dirichlet boundary conditions. It's easier, but you still have to be careful with it. And that shows up when you do this kind of things. So let's first go to interface elements. And I go back to this example which I showed for the traditional interface elements. Here an interface, pre-put, here a notch, and well, here we go to more stiffer behavior. And in fact, for interface elements, one of the remedies which is now known and which is often used and also implemented in most commercial packages is that for interface elements you don't use Gauss integration, but you use Newton-Cotes integration or Lobato integration. That helps. Well, unfortunately it doesn't help for isogeometric analysis. So we looked here at this beam, where here we have the notch and here we have interface elements. And then we looked at Gauss for low stiffness, all fine. We got huge oscillations for high stiffness, much bigger even than with traditional interface elements. And in fact, this is what I call the curse of higher order interpolation. In these cases, a higher order interpolation, more smoothness does not help you. At some point, I also did a calculation with a shell element, a thin shell element, where you get wrinkling. In this case, the standard finite elements converged much faster than when we had an interpolation using NURBS. And the reason is, when you have wrinkling, when you have the possibility to have a bit of kinking at the C0 continuity line between elements, that helps you. I mean, it's not the good way, in fact, you make an error to an error, but it helps you. Well, if you do it totally properly, using the right continuity with NURBS, it converges slower. So, it doesn't always help. The problem is now even that with Newton-Cotes it doesn't work. So the only way where we could get it working is when we had here a lumped integration. So only then, with nodal integration, we got it right. Don't ask me how, why exactly. This is just trial and error. Now, this is regarding knot insertion. So we start with a case where we have the blue interpolation. These interpolation functions. So we use these nodes. Now you see that at this point, at point 5, we have a C0, so this should be, sorry, this should be C0 continuous. Typo. This should be C0 continuous here. I mean, the function is continuous, but we have a kink. How can we make this into a jump? Well, we just multiply the number of degrees of freedom at this point, and then we add essentially a direct type function for the stress. We add a jump there. And this is a way which in nerves is very easy to realize. So this is an example of that. Here we have epoxy. Here we have a hard fiber, and we have an adhesive layer here, which is loosening up at loading. You see here the meshes upon mesh refinement, you get very quick conversions. This is another case where we have really followed a crack and adapted the mesh to that. The advantage is you have a much smoother stress field and therefore a very good prediction of your crack direction. Here you see the crack, and here you see the gray area, you see experimental evidence. Another one where we have a double notched specimen, cracks propagated like this, and here we have, no, we don't have here. The point is, this is one where we have still some issues, which is related to the fact that it's very difficult to mesh such a domain with two cracks. To propagate cracks such that they really cross mesh lines is difficult if you don't have XIGA. And then you would have to construct this like in cut packages of multiple patches. The problem is then that you have a patch here, a patch here, a patch here, a patch here, one here, one here, one here, that you have zero continuity lines here which destroy exactly what you want. So this is something we are currently working. Now finally, splines, B-splines constructed on triangles. So here we have the black triangles, the big black triangles, which we have just a normal linear interpolation. And we split each of these triangles into 6 mini triangles. And then we construct these green points, and we make red triangles around each of these nodes. And then on these red triangles, we can construct splines, which are then smooth across these elements. Now, this works enormously well. There are some problems. This exact capturing of the geometry is not possible. The order elevation, as you know, is not as easy. And the extension to 3D is not rigorous. But you can do very nice crack propagation. Here you see again the notch specimen, and you have a curved crack propagation with easy, very easy standard remeshing. And here you see the stress profiles, very smooth, very continuous, and the convergence when you go to a higher number of degrees of freedom. Another case, this case of the Nora Mohammed specimen with double notches. Here you see the crack propagation with the stress contours, again, smooth contours, well defined, and these are just the advantages of these approaches. Also the crack propagation paths are in agreement with the experimentally measured ones. So, in sum, isogeometric analysis has promise for discrete fracture. There are 4 potential approaches. At the moment, each with its advantages and cons. You can use NURBS or T-splines with non-insertion. It's enormously elegant, fits excellently with all concepts. You are somewhat restricted to the crack path. Powell spin B-splines, very straightforward. If you can arbitrary crack paths, you can use traditional remeshing schemes. The disadvantage is that it doesn't really conform with the isogeometric concept. And also, it's not really totally, it's not evident how you can extend it to 3D also for unstructured meshes. Isogeometric interface elements, very easy to formulate. The disadvantage, as with standard interface elements, is that you have only for predefined crack paths and for spurious traction isolations, you have to do some special measures. And yeah, finally, extended isogeometric analysis, a beautiful blend in principle of XFEM and IGA. There are some results published in the literature, but they are not really, I mean, there are some drawbacks if you really go dive into it. We are working on it to make them better, and it could become a very nice development. So I think that was what I wanted to tell you. Don't expect that you have necessarily understood all the details, but it's giving you a flavor of what is possible, and I've tried to sort of warn you for some of the pitfalls and show you some of the avenues to possibly go. Thank you very much.